Okay, let's get started here. About 1 a.m. last night, I finished grading, and I sent all of you back your projects, along with posting an answer key to the course website. So I'm sure all of you have taken the time to look at it. We will briefly talk about project number 1 in the grading shortly. Project number 2 I have here listed as today we would discuss. Unfortunately, that will not happen. Ended up taking me 8 hours to grade project number 1, and some of that time I had originally budgeted to putting together project number 2. So I hope to finish putting together project number 2 Thursday or Friday. Test number 2 is Monday, October 28th. And notice since this Monday coming up, October 21st, is fall break. That means we only have one more class after this one before test number 2. So that means we will review towards the end of class, our next class. So please be prepared to ask questions if you may have them regarding test number 2. Are there any questions before we get going here? Okay, so project number 1, let me bring up the listserv posts. Overall, the grades were mostly they were good. I do appreciate you, most of you taking the time to nicely organize your projects, because that did make it easier for me to grade, despite it taking 8 hours. But I am concerned with some of the students that were, let's say, less than 80% on the actual project itself. And here's the reason why I am concerned. Here's a typical distribution, or I guess a typical scatter plot for when I use this projects and tests format in an applied stat course like this. This is the typical scatter plot that I see of projects versus tests. And what you see here is that there is a large number of students that are clumped with very high grades in terms of both projects and tests. But as a student's project's grade gets lower, we can see that their corresponding test grade drops more than the same amount of drop with the project's grade. So what that means is that typically students will score higher, sometimes even much higher, with the projects than they will with the tests. Given that here's from the syllabus, that 25% of your grade is the projects, essentially projects portion of your overall grade, and the remaining is the test, that is very concerning then, that if you end up doing, let's say, a C or lower on the project, well, typically, that means that for a test, you would definitely do C or lower, probably D or lower. This is what I typically see. It doesn't happen in every case, but usually a student's project grade is higher than their test grade, unless they are scoring extremely high on both projects and tests. So, similar to what I said with test number 1, if you got a C or lower, you should be concerned, and you should reassess how you're approaching this course. If this is happening now with the projects, again, with project number 1, again, you need to reassess how you're doing this, because you are not getting the material as well as you should have. You're not performing as well as you should have. Do note that I do not scale any grades at the end. The grade that you get is the grade that you earn. So if you get a 75% as your overall grade for the course, that means that's a C. Okay? Are there any questions regarding that grading aspect that I just discussed? Okay, so there are a few comments I want to make about the project specifically. First of all, please make sure to read through the entire answer key, even if you did perform well on the project. The reason being is because I might have answered a problem differently than what you had. And, sometimes what I encounter when I'm grading a project I see a student's answer, I see, well, yeah, it is essentially right, but maybe it could have been answered better, and so maybe I didn't take off points for it. So the reason why I say this is that, at least in my answer key, often the way, or usually the way that I answer the problems is what I see is the best approach, or the best answer that's possible. And so I do recommend that you read through the entire answer key, even if you got every, even if you did well on every problem. Let's see here. Sorry, let me get my notes out. Some of the commonly missed problems were, for example, most of you chose 4 principal components. On my answer key, I said 3 is justifiable. 4 might be a little bit better. I said 3 or 4, but most of you chose 4 principal components. The problem that I often was seeing then is when you were actually displaying a plot of the principal component scores, well, you might only have shown the first 2 or 3 in your plots. Well, if you're choosing 4 principal components, you're seeing that that 4th principal component is important. So why aren't you plotting that? And so unfortunately, then some students lost points because they didn't include any kind of plot of that 4th principal component. There was for those who did, there was a number of, I guess you could say, creative ways that they were able to include a 4th principal component on a plot beyond than what we even have talked about in class. But at the very least, you could do a parallel coordinate plot to show that 4th principal component. Do note that it is still okay to do a plot of just 2 principal components or 3 principal components. But you at least needed to say that this is not necessarily showing all the information that's available to us, or that we would prefer, because we actually had chosen 4 principal components. Let's see what else. Those of you who use 64-bit R, you will have gotten the 4th principal component. Those loadings would be basically the negative of my version of the loadings, because I use 32-bit R. But otherwise, as long as you interpreted the problem, that interpreted the principal component correctly, that was fine with me. Okay, I guess that's enough. Any questions? Obviously, you may not have had enough time to look through it before our class today. So, I'm sorry I wasn't able to get it to you sooner. But in the next week before our next class, if you come up with some questions about it, please feel free to post a question to the listserv, or be prepared to ask a question during our next class. Okay. With that, then, if there are no questions regarding the project, let's continue in the notes. Just to review a little bit where we were at, we were talking about factor analysis with respect to the goblet data. Here's what our estimated factor analysis model was. So what we have here, let me pull up my red pen. So what we have here is the standardized variables, and we're saying that these standardized variables come about through this particular model structure, where we have our factor loading matrix, and that basically allows us to find linear combinations with our common factors. In this case, we only had 2 common factors. And of course, this factor loading matrix, since it's allowing us to form these linear combinations, the lambda hats that are assigned there really help us determine what these common factors are actually measuring. So if I have a lambda hat that is, let's say, close to 0, then that says that that corresponding factor then isn't playing a big role in determining what z is. So when I interpret that common factor, then I wouldn't include that particular z in the interpretation. So then we add that to then our specific factors, the etas, which basically account for all the other information that's not necessarily accounted for by these common factors. Now, in order to estimate this model, we use the following relationship here. Based upon our factor analysis model, we could write our covariance matrix like this, where P is our correlation matrix. Lambda is our factor loading matrix, not the estimated version, but the actual version. And psi is a diagonal matrix with the specific variances of the etas on the diagonal. And so this is what we use to use then in the process of maximum likelihood estimation in order to come up with estimates for the lambdas and also for the psi 1 through psi p specific variances. Now, the reason why I bring this up is because it allows us then to come up with a way to evaluate the fit of our model. All of you have seen regression models before, and you've seen with regression models, one way to evaluate the fit is to look at the residuals. And with these residuals, the closer they are to 0, essentially, the better the fitting the model. In the extreme case, if all the residuals were 0, and that says, hey, your model's really explaining everything possible about your response variable y. So it makes sense then to think about how we could evaluate the fit of our factor analysis model by looking at some kind of residual. And that's where we left off last time, was to look at the residuals. Let's see, where are they? Here we go. So what we can do is look at this capital R matrix. This is our estimated correlation matrix that comes about through using the usual formulas for correlations that was presented in the data, distributions, and correlation section of our notes. And we take that R matrix and we subtract off essentially what our factor analysis model says that the estimated P, the true correlation matrix, should be. So again here, what would you like these values to be? Would you like them to be large or small? You like them to be small. You like them to be close to 0. The closer they are to 0, the better the fitting the model. The better the model fits the data. Okay, so let's talk about how then we can come up with this matrix of residuals. And unfortunately, I had accidentally closed out my program here, so let me find it. Wait a second. Closed out R for some reason. Okay. I'm going to read in my data. I'm going to estimate my model with the factNL function. We're going to use 2 factors. Okay. So, first of all, how can we find then the estimated correlation matrix using the stuff that we learned with the data distributions and correlation section? Well, it happens to be given to us in the results for our factNL model. If we put the results in mod.fit2, we can extract the correlation component, and there's our estimated correlation matrix. So this is R. Now, in order to find then the lambda hat times lambda hat prime plus the psi hat matrix, what I can do is I can go to a particular component that's in mod.fit2 called loadings. Now, this is actually going to return a few different things to us. And the syntax is then kind of odd here, but in order to just extract the matrix itself, I do a bracket, comma, and bracket. Well, remember, we've seen this kind of syntax before. You know, for example, if I were to do this here, where I would just have a 1 as the second index, you could say, that will return just the first column of a matrix or data frame. So it's logical to think then that if I were to just put nothing in there in terms of no numbers, I would actually return the whole matrix. And indeed, that's what happens. So there's my lambda hat matrix. So then what I'm going to do, use matrix multiplication. So I'm going to take it times the transpose of lambda hat. And then to do a diagonal matrix in R, I can use the diag function. And remember, the specific variances are often also called uniqueness in some books and in fact in some software packages. So the specific variances are listed there that we actually pointed out last time. So when I use the diag function with that, now I have my diagonal matrix. So let's put this all together. And so my factor analysis model says that this is the estimated correlation matrix. And what I would like to do is be able to compare that to if I were to essentially not use a model at all. Compare it to the R matrix. So to do that, I can just simply subtract the two. Okay. So I'm going to subtract these two results. I'm going to round to 4 decimal places and make it look a little bit prettier. And this is what I get. So what do you think about the fit of the model? Remember, correlations are between -1 and between -1 and +1. So we do have kind of a scale that we know of for these residuals. So what do you think about the fit of the model? Yeah, it's decent. You know, the only thing that might be a little bit concerning is this right here. Comparing the W5 and W6. Of course, correlation matrices are symmetric, so that's why you also see the same information displayed here as well. But overall, I'm pretty satisfied with the fit of this model. Not perfect, but you should never expect a model to be perfect. It's pretty good. I'll show you an example shortly of a model that doesn't fit very well. Now, make sure I'm talking about everything I need to. Yes. Now, there might be cases where you have, let's say, a larger number of variables. You know, in this case, we only have 5 original variables. There might be cases where, you might have 10 variables, or even 15 variables, or even more. And look at all the elements in one of these matrices here could be kind of difficult. And so it would be nice if maybe we could somehow summarize, let's say, some of these differences that we should be worried about, where what the usual estimate of the correlation matrix tells us versus what the model tells us for the estimate of the correlation matrix. When should we be worried in terms of their differences? So here's some additional code that you can use then to make this comparison a little bit easier. I'm going to put the results from finding these residuals in an object called resid2, two factors we were using. And what we can do is, and let me just actually go ahead and do that part right now. And so what we can do then is, how about we just look at the absolute value of each of those residuals, because after all, we're looking at how far each of them are from 0. And then maybe we could just say anything greater than 0.1 for those absolute values may be a little bit concerning to us. So by taking a look at the absolute value of these residuals and putting a greater than there, what this is going to tell R to do is do a logical check. And it's going to check every single element in this absolute value of the residual matrix. And it's going to return trues and falses. So we can see at one particular place that we had pointed out where I have a true, W5 and W6, that combination. And we can even go a step further here and say, well, how about we just sum all those trues and falses? You might be thinking, wait a second, how can you do math on trues and falses? They're trues and falses. They're words. They're not numbers. Well, in R, a true is represented numerically whenever you give it whenever you use it in a mathematical formula. A true is represented as a 1. A false is represented as 0. So if I use the sum function to sum everything up, notice I get 2 because I had a true here, I had a true there. So again, I'm not worried about 2 combinations of the variables. I'm only worried potentially on 1. Because remember, correlation matrices are symmetric. So this always should be an even number. You can go a step further, and this is actually what SAS does. And you could, let's say, look at the column means in that matrix that we had just seen. So what I could do is maybe find, well, what is the average deviation represented by a column? So if I use COL means, that finds the column means, and we can see that only the last two columns are, on average, maybe a little bit farther from 0. Why is it the last two columns? Again, it has to do with the W5, W6 combination. Okay, so again, I got that idea to look at that from SACS. Okay, so that's one way to evaluate how well your model fits the data. Are there any questions? So now you might be asking yourself, well, how do we determine how many factors we should choose? Well, I just showed you how to evaluate the fit of a model through these residuals. So you might be thinking now, maybe I could fit a few different models in terms of maybe one factor, or one common factor, two common factors, three common factors, and look at these residuals. And if I get to a point where I'm satisfied with the size of these residuals, then that will tell us, well, which number of common factors I could use. So that is one way to do it. Let's talk about maybe a little bit more formal ways. In particular, something called a likelihood ratio test. Now, again, depending upon your background, you may or may not have heard of likelihood ratio test before. I would imagine a large number of you have. But if you look just strictly on the prerequisites for this course, a likelihood ratio test may not have been presented. Like if you only had set 801, they would not talk about just likelihood ratio test in there. So let's talk about what a likelihood ratio test is first. And so in this maximum likelihood estimation supplement that I put together, that's on my website, I have a general description, or short description, what a likelihood ratio test is. Okay. So LRTs, likelihood ratio tests, is a very common way that people use to perform hypothesis tests when maximum likelihood estimation is used to estimate some kind of parameters. Very, very common method. Very useful. And if we look at the name, likelihood ratio, you would expect to see some kind of ratio between likelihoods. In fact, that's what it is. So typically, this ratio is represented by the Greek letter lambda. Please don't confuse that with our factor loading matrix, which we also have called lambda. I'm just presenting here in a way that's most commonly done. And here's the two likelihood functions. In the numerator here, we're going to have the maximum possible value of your likelihood function that you could have as long as HO is true. So, of course, HO usually has some kind of restriction on your parameters. And so, given that restriction, find the maximum possible value of your likelihood function. Put that in the numerator. And then the denominator, we're going to look at the maximum possible value of the likelihood function when either HO or HA is true. So, either or. So you can see that this is going to be a little bit less restrictive. And what ends up happening then is the denominator will always be greater than the numerator, because the numerator essentially is a special case of the denominator. And how close that numerator is to the denominator, in other words, how close this lambda is to 1, gives us some important information about the truth of the null hypothesis. Now, a long time ago, it was shown that if I take a little mathematical transformation of lambda, and if HO was true, then the distribution of negative 2 log lambda is approximately a chi-square distribution, as long as you have a large sample size. For those of you who like a more mathematical description of that, this is the way that it would be presented, for example, in a class such as Sat 980. Negative 2 log lambda converges in distribution to a chi-square distribution. If you don't want that kind of a mathematical description of it, just think that for a large sample, a chi-square distribution is going to work. Okay. Now, the degrees of freedom, of course, there's always a degrees of freedom associated with the chi-square distribution, as you would learn in a Stat 801-like class. And simply the degrees of freedom is this. How did I actually write? I wrote it out a little bit differently. So the number of unrestricted parameters if HA is true minus the number of unrestricted parameters if HO is true. I phrased it in a more mathematical way there on page 8 in my notes. I think this is a little bit easier way to think about it. And if this is still not clear what that means, I will have an example very shortly that will explain it very, very well. Okay. Note that this is going to be a right-tailed test, meaning that we're looking for large values of -2 log lambda in order to decide if we're going to reject or not. We can compare then this -2 log lambda to a critical value from your chi-square distribution, like a 0.95 quantile. Okay, so let's take a look at an example that applies this. So this is that field goal kicking example that we looked at last time. Let's say I want to test. The probability of success on a field goal is 0.5 versus it's not. Okay? Well, you've seen hypothesis tests just like this for proportions in Stat 801. You just may not have seen it with applying the test with a Likert ratio test before. Okay. So again, with this Likert ratio test, I need to find two things, a numerator and denominator for lambda. So the numerator says, let's suppose that HO is true. What's the maximum possible value of that Likert function? Well, so I've written out my Likert function here, assuming HO is true. So wherever I saw a pi before, now I have a 0.5. And remember how I have the sum of the y's, the number of successes, and also I have n minus the sum of the y's, the number of failures in the Likert function for what we saw before. If you remember, this was equal to 4, and this was equal to 6. So the maximum possible value of my Likert function, if HO is true, is very simple to find here. It's 0.0009766. Well, what's the denominator then? The maximum possible value of the denominator, assuming either HO or HA is true. So what's the possible range for pi now? What's my restriction on pi? 0 to 1. Okay, well that's, any kind of probability, that's the restriction. So essentially I don't have any restrictions at all on pi if HO or HA is true. So what's the maximum possible value of my Likert function? Well, it comes about through plugging the maximum Likert estimate that we saw last time into my Likert function. Because we've already found that maximum possible value, and it was 0.001194. So I simply put both of these values in there, and I get 0.8179. Remember that this is a ratio. So if I take -2 log lambda, I get 0.402. I can find a 0.95 quantile from a chi-square 1 distribution. The reason why there's a 1 degree of freedom is because notice the number of unrestricted parameters that's in the alternative hypothesis is equal to 1. The number of unrestricted parameters in the null hypothesis is 0. So that's how I figure out my degrees of freedom. Notice there's only one parameter, essentially, with a Bernoulli distribution, and we are restricted in HO. So unrestricted parameters, 0 in HO. So the corresponding critical value is 3.84. Easily find that in R. Hopefully you wouldn't want to go to a statistical table. That was something we did in the 1990s. Hopefully you didn't learn to do that. In R, we can use the Ksq function, quantile, chi-square. Put in 0.95 as a quantile, 1 is a degrees of freedom, you get 3.84. Okay, so like I said, it's a right-tailed test. So because 0.4 is less than 3.84, my critical value, I say do not reject HO. There's not sufficient evidence to say that pi is any different from 0.5. Okay. To put it in a graphical sense, this is what we did here. Here's the chi-square distribution, roughly speaking. Alpha, suppose we make alpha, well, I guess I already did that, alpha, say 0.05. And this is what we had here. My quantile is 3.84. Here's my test statistic. It fell over here way on the left-hand side. Okay, so I have some questions here. Let's actually talk about the first question. Again, this number is always going to be, this lambda is always going to be between 0 and 1. So suppose the ratio, let's look at the second question. Suppose the ratio is close to, is close to 1. What does it say about HO? It's likely to be true. Why? Okay, let's talk about what a Likert function represents. It represents, it's measuring, essentially numerically, how plausible values are for your parameters. The larger the Likert function, the more plausible the set of parameter values that you put in your Likert function are. So what this is saying then is when I'm taking this ratio, and if it is close to 1, that says the maximum possible value of the Likert function when the parameters satisfy HO is very close to the situation of the maximum possible value of the Likert function when the parameters satisfy either HO or HA. So it sounds like then what you're saying in HO is very plausible. Because now when you don't have that HO restriction, you're getting about the same Likert function. So lambda will be close to 1. Then suppose the ratio is close to 0. What does it say about HO? Well, the corresponding parameters that you have in the null hypothesis, what's set to, are probably not very plausible. Because the Likert function is a lot lower than if you remove that restriction. Well, what does this mean then in terms of -2 log lambda? I could do a simple demonstration here. So if I go -2 times log of, let's say some number close to 1, let's say 0.9. Now, again, this would be a situation where what we say in the null hypothesis seems to be correct. Look at its value. It's small. Suppose I even go up to 0.99. Again, it's small. It's even getting smaller as that ratio is getting closer and closer to 1. Instead, suppose we look at 0.1 as the value of lambda. Notice how now what's happening there? -2 log lambda is getting large. Suppose I go 0.01. It's getting even larger and even larger. So you can see then why we have a right-tailed test. We reject HO when this -2 log lambda is large. Okay? Is there any questions? Okay, let's apply this likelihood ratio test technique to factor analysis. So this is now back on page 24. And this is the hypothesis test that we're interested in. The null hypothesis is that the m factors that we have chosen are sufficient. This is my model. I have these m factors. This is my model. Note that I have written this in terms of my factor analysis equations here, where I have a sigma. You could also replace that with P2. It's just I happen to write it in terms of sigma. The alternative hypothesis is, oh, wait a second. You're going to do better if you have more common factors. Okay? Now, one could go through a mathematical derivation of -2 log lambda. And actually then prove that it has a chi-square distribution for a large sample. You're not responsible for that. Instead, rather, you're just responsible responsible for how to apply this Likert ratio test to a factor analysis situation. My negative 2 log lambda looks like this if you were to go through all the math. Note that I actually put a delta here versus a lambda because, of course, our factor loading matrix, when we're doing factor analysis, is called lambda. So that's why I chose to change my lettering. In the end, you can actually get a better chi-square approximation if you use what's called a Bartlett correction. And so my negative 2 log delta with this correction essentially is replaced by, for the lack of a better symbol, A. So there's what this statistic looks like. For a large sample, it can be approximated by this chi-square distribution. And we reject when A is larger than the, let's say, 0.95 quantile from this chi-square distribution. So again, if we reject, it says, okay, you need more common factors. Your model is not sufficient that you have specified. Now, another way to choose, to help you choose the number of common factors is to use what's called a Ksq information criteria, or AIC. I've seen this used a number of times with factor analysis models, but unfortunately, R doesn't provide us a convenient way to calculate it, which is it's quite unfortunate because SAS does. Of course, what one could do is actually program in the corresponding equation that you see there. I guess because of time considerations, I decided not to, at least this time around when I teach the course. I think in total, putting together these notes for factor analysis took me at least 30 hours, maybe 40 hours. And given that I had so many other lectures to also prepare this semester, you have to cut somewhere. You can't always write functions to do everything that you want to do the first time around when you teach a course with a new software package. So I decided not to use the AIC this semester. But I at least wanted to let you know that it is possible. If you want to know more about using the AIC, I'd be happy to discuss it outside of class. Okay, so let's apply this Likert ratio. Oh, I'm sorry. There's something else I need to say. Okay. Unfortunately, when using Likert ratio tests, the test is often what's referred to as too powerful. Meaning, it will say that you need more common factors than what's really necessary. So that's a consideration when you look at some of these, when you do this hypothesis testing, that's a consideration always have in the back of your mind that this test often says to use too many common factors than what's actually needed. Okay, so please be aware of that. Okay. So let's apply this now to the goblet data set. So if we look at the output that we get from using the print function with our mod.fit2 object that we got from factor now, this is the output that we get. And at the very bottom, we have the necessary information that we're looking for. So it's the test of the hypothesis that 2 factors are sufficient. That's the hypothesis test that we talked about. The chi-square statistic using the Bartlett correction. So our A is 4.74. There's 1 degree of freedom. And so if you do the chi-square approximation with this and calculate a p-value, just like I would normally calculate a p-value for a right-tailed test, you get 0.0294. So we see that this p-value is a little low. Now it's kind of borderline, because if you use alpha 0.05, you would say reject HO. If you use alpha 0.01, you would say don't reject HO. So because of that, I typically, actually when I use hypothesis, I typically don't state a particular alpha level. And instead what I would say in this particular situation, there's moderate evidence. It's not extremely strong, but there's moderate evidence that if we were to trust the result from this hypothesis test, that we need more common factors. So 2 might not be enough. Okay. Well, let's look at what happens if we use a different number of common factors. So let's look at what happens if we use just one common factor. Now, given that p-value that we just saw with two common factors, you probably would expect that one's not going to be any better. In fact, you probably think that one's going to give you a lower p-value. Let's look what happens. So I'm going to estimate my model with one common factor. I'm going to put the results into mod.fit1. Notice the factors argument. I put equal 1 there. You can extract the p-value from this object that you get from factor_now by using p-val, that component of mod.fit1, and I get a p-value of 6.6 times 10 to the negative fifth power. So indeed, my p-value is much smaller. I need more common factors than just one. And to help illustrate the point even further, here are my residuals. Now, if you're finding that your model is not fitting the data well through this Likert ratio test, you would expect to see residuals that might be large relative to a correlation scale, -1 to 1. Well, take a look at this. Take a look at, for example, those two residuals there. One of them is 0.5560. Again, correlations are between -1 and 1. 0.5560, that's a big part of that possible range. So, by looking at the residuals, we see that our factor analysis model is not sufficient with only one common factor. Okay, so well, what happens if we try three common factors? So, I put the results into mod.fit3. I say factors equal 3, and then we run into a problem. 3 factors are too many for 5 variables. This now relates to some of the problems that I was illustrating to you last time with these factor analysis models. Due to the number of parameters that we need to estimate with this kind of a model, the more common factors you add to your model, the more factors that you need. You just might not have enough of these, corresponding correlations, if you remember our discussion from last time, to really be able to do the estimation. And in fact, if you actually look at that corresponding degrees of freedom, I know I didn't necessarily discuss it directly here, but this is the actual formula that one would use to find the degrees of freedom for this test. You get a negative degrees of freedom. Can't work with negative degrees of freedom with the distribution. So because of that, we cannot use 3 common factors. So even if we wanted to use more, we can't. Given the results that we saw with the residuals, though, I'm not necessarily disappointed that I can't use 3. So I thought the residuals looked pretty good. And also the fact that these Likert ratio tests can be overly powerful. And we kind of had a marginally significant result. So 2 common factors, I think, is sufficient. Are there any questions? Okay. Speaking of problems with factor analysis models, here's what some people think is a problem. Other people think it's a great aspect. I'll let you make a decision. Hopefully my bias will not influence you one way or the other. So if I choose a number of common factors that's greater than 1, my factor loading matrix is not unique. What that means is that the corresponding estimates, well, let's not necessarily phrase it that way. What that means is I could use a different lambda matrix and have essentially the same model in the end. In terms of, let's say, my factor analysis equations and what lambda times lambda prime plus psi actually ends up being. And remember how that is used then when we determine what our maximum likelihood estimates are, for example. So why? And the reason why that's so important is that, remember, with our factor analysis model, in order to interpret what the common factors represent, we look at the lambdas. So if the factor loading matrix, my lambda, is not unique, meaning I could have different lambdas and have essentially the same factor analysis equations, hopefully you see a potential problem. Because my interpretation of my common factors will change. depending upon what the factor loading matrix is. So here's what really illustrates the potential problem. Let's let T be M by M orthogonal matrix. And remember, as we have discussed previously, orthogonal matrices have this nice little result. And that is if you take T times T prime, you get the identity matrix. Okay. So here are my factor analysis equations expressed in terms of my correlation matrix. So step 1 here, I just simply state what the equations are. Step 2, I'm going to slip a T times T prime between those two lambdas. I'm going to slip it in there. Now, am I changing anything? No. Right, I still have the same equality there. Because remember, T times T prime is the identity matrix. So that means lambda times the identity matrix, it's lambda. So it's kind of like this, to illustrate the point. Suppose I have 3 times 6. Of course, that's 18. Suppose I have 3 times 1 times 6. Well, that doesn't change anything. You still have 18. Essentially, that's what I did, but now in a matrix format. Then now let's rearrange stuff. How about I put lambda and t together? So note that at t prime times lambda prime, there's a nice little result from matrix algebra that says the following. If I had A times B transpose the whole thing, that's equivalent to B transpose times A transpose. So I just use that result. If you don't believe me that it's true, just stick some matrices into R and actually try it to see what happens. How about now we call this lambda times T lambda star. And so essentially what I have here now is my factor analysis equations. All I'm doing is just using a different factor loading matrix. That's it. Everything's still going to equal the same thing it was before, but I have just a different factor loading matrix in there. Well, why is that a problem? Well, again, remember, we use these lambdas to help interpret what the common factors represent. So if I have a different factor loading matrix, that means I have a different interpretation of the common factors. Also, there are an infinite number of possible orthogonal matrices that one could put in there. So there are an infinite number of possible interpretations that you can have for your factor analysis model, as long as m is greater than 1. Okay? Let's relate this now to the factor analysis model. I wrote it in terms of x tilde. I could have simply wrote it in terms of z as well. I just chose x tilde. Well, let's again put in that t times t prime inside of the equation there where we have lambda and f. Let's use properties of matrix algebra so I can rewrite it. And then set lambda star to be equal to lambda t again. And how about we call t prime times f, f star? It's just a different common factor, vector. Now, through the use of this little trick here, or I should call it a trick, this little mathematical result here, now I have different common factors. Same model in the end, different common factors. Note that I have put on test previously maybe actually ask students to go through something like this on a test, or to go through something like this on a test to illustrate the fact that we have potentially different interpretations of our model. Okay, so by multiplying lambda by an orthogonal matrix, this has a special name in factor analysis. It's called a rotation. And the reason why it's called the word rotation is that there's actually a graphical interpretation that one could look at to understand better what's happening here. And we will take a look at the graphical, or we will look at the graphical interpretation shortly, although we won't necessarily get into the details. What one can actually show is that this T matrix here is, especially in the case where you have two common factors, this T matrix can be actually written in terms of sine and cosines. And that allows you to do some rotation of your x, y axes. Okay. So, therefore, a researcher could perform rotations, meaning find different T matrices, to find an interpretable set of factor loadings until they find an interpretable set of factor loadings, or in terms of they find the interpretation that maybe perhaps that they want. This is the problem that some people have with factor analysis. So, as I say here, this is both a good and bad outcome. Hopefully you see what the bad outcome is, that you can come up with an interpretation that you desire. That's not necessarily what's good in research to do. But it's good in terms of that, you could find maybe a better, easier interpretation. The goal, though, is that you want to find a T matrix such that this new factor loading matrix, this lambda star, leads to loadings that are close to 0, close to 1, or close to -1. Why? Well, we've already seen this when we looked at the factor analysis model that we had already had before, where we had a particular factor loading, a particular lambda that was close to 0. And that helped us in our interpretation. We didn't need to, I think, include, for example, Z4 to interpret the second common factor. So ideally, we would like to find a lambda star that has lots of zeros, lots of numbers close to 1, lots of numbers close to -1 in it. You'll see how we do that shortly. Okay, so now here's the graphical interpretation. You're not responsible for the math behind the graphical or why we can think of this stuff in a graphical way. I've talked about it once or twice in the class before, and I don't think it's really worth our time to do it. But I think that the general concept of this graphical way to think about this is helpful so you understand what a rotation means and what the goals are of a rotation. So with our factor analysis model, our estimated factor analysis model, we have this for our lambda hat matrix. Okay? And what I'm going to do is graph this lambda hat matrix in a particular way, where I'm going to put the corresponding lambdas for factor 1 on the x-axis. I'm going to put the corresponding lambda hats for factor 2 on the y-axis. So essentially, for example, I'm going to plot a point at 0.55 and 0.73 on my plot. And I'm going to label it with W1. That, makes sense because that's the corresponding lambda hats for W1. I'll let you look at the details of the plotting code on your own. It's very similar to what we've used before. And here's a plot of those factor loadings. So if you remember again, W4 had a factor loading for the second factor that was close to 0. And what that meant for us, it was easier than to interpret the second common factor, because we didn't need to include, let's say, W4 in our formulation of an interpretation. Okay? But, unfortunately, this easier interpretation only comes with W4. What would be nice if perhaps maybe there was some way that maybe we could adjust these factor loadings so we have more of these easy interpretations. And the way that you can do that is to rotate your XY axes that you see there. So what I'm going to do, and this is illustrated on the next page here, 32, I simply rotate, maybe about 40 degrees, the XY axis. So here's my X-axis from before, and here is my Y-axis. Oops. Nope. This is my y-axis from before. Okay. Now what you could do is, given this new xy axis, you could find what the corresponding lambdas should be for W2 and W1, for W6, for W4, for W5 as well that you see plotted there. And hopefully you realize that, notice that W1 and W2 are going to have values of lambdas that are close to 0 for the x-axis. Large values corresponding to the factor 2 for the y-axis. W6 there is going to have small values close to 0 for the y-axis, which would be for corresponding to common factor 2, and values closer to 1 for the x-axis, corresponding to factor 1. And so thus now, our factor analysis model will be a little bit easier to interpret if we simply choose those corresponding lambdas. And so essentially what this T matrix is that allows us to do the rotation, well, like I just said, what this T matrix does, it basically allows you to rotate your axes in this manner. And we want to choose a T matrix that gives us something that looks like that. Are there any questions? Okay. Let's move on to page 33 then. So let's look at specific ways to find this T matrix. And so we're going to do a small subsection here called orthogonal rotation methods. The reason why it's called orthogonal is because we are still going to keep, essentially these perpendicular axes here. An x-axis and y-axis that are perpendicular to one another. The word orthogonal is used because, suppose you have 3 common factors, 4 common factors, 5 common factors, and so on. You cannot necessarily think of it in terms of just a 2-dimensional perpendicularness, if that's a word. Anyway, the most commonly used rotation method is what's called a Varimax method. So notice the word there, Varimax. Maximize variance. You'll see how we maximize a particular variance shortly. So let's take a closer look at lambda times t. Again, the goal is to find a t. Before I had called this lambda star. For notation purposes, it's going to be easier for the stuff that I'm doing here to make this something that's a nice letter that doesn't have anything in the superscript. So how about if I just call this matrix B instead? Not B for builder, just B. And so, of course, this is what the B matrix would look like. So the 1-1 elements, B1-1. 1-2 elements, B1-2, and so on. A long time ago, someone suggested to find a T matrix. Again, remember, B is a function of T. Find a T matrix that maximizes the following expression. Let's call this expression B star. Now, the first time you look at it, you might be thinking, geez, that is an odd expression. Why would someone even come up with that expression there? But actually, it makes sense why one does. Now, in Statistical 1 course, of course, you will learn about a sample variance. Let's say our data is represented by x's, and you use usually the notation of s squared to mean a sample variance. And to find a sample variance, you would take sum I equal 1 to n, where n is your sample size, xi minus x bar, the sample mean, squared, divided by n minus 1. Right? Okay. Now, another version of this estimator is if you just put an n there instead. This is the usual biased estimator of a sample variance. We kind of discussed that earlier in this course. And what you'll learn, most likely in a Statistical 1 course, is that you could rewrite this expression through using some simple algebra. You could rewrite the expression like this. N, the sum I equal 1 to n of xi squared, minus the sum I equal 1 to n of xi, that quantity squared, and also divided by n. This is often presented as an easier by hand formula to use to do the calculation, if one actually uses by hand formulas anymore to calculate a sample variance. This will be the by hand formula. Okay. So essentially, now compare that expression to what we have here inside this parentheses. See some similarities. Focus on a particular column of my matrix B. Excuse me. Now imagine the values in that column are each squared. And so then essentially, work for me, computer. So essentially, what we see here for the old sample variance formula is essentially what you see there for b squares. So everywhere you see an x, replace it with a b squared. And so what we have with inside this big parentheses for this v star, we have simply a variance calculation for squared elements in a column of your B matrix. Does everyone see that? And since we have m columns to our B matrix, how about we sum them all up? So we're having the sum of variances. And remember, what this Kaiser suggested in 1958, a long time ago, was to find a t that maximizes this. That maximizes this sum of variances for squared elements in the columns. Why would we want to do that? Well, first of all, remember the values in this B matrix are going to be between -1 and 1. Okay, remember, relate this to what our lambda matrix was originally. We showed last time values were between -1 and 1. So if I always would square them, what's the numerical range that I have? 0 to 1. And if I try to maximize the variance within each of the columns, what does that say then? Or how would you maximize that variance? Choose elements that are close to 0 and close to 1. In other words, on the extremes. So again, what this method does, this Varimax method does, it chooses a t that essentially tries to make our b's in this B matrix, tries to make them as far apart as possible. The farther apart they are, the more zeros we will get, the more ones we will get, the more negative ones that we will get, and then we'll be happy because we'll be able to interpret our factor analysis model better or more easily. That's the motivation behind doing this. Of course, a short answer question on a test might be to say, describe the motivation behind this V-star statistic. Now, what ends up happening, though, is that we use a different, instead of using V-star, we use a V. And it's not really that big of a deal, but we just make an adjustment to these B's to take into account the communalities of the, remember the sum of these lambda squares. Take them into account when we do this maximization. But in the essence, it's the same basic idea, so that's why I start with V star. Okay. So I have a fill-in-the-blank question here. So I know, sorry, I'm using a little bit of a different notation. Core meaning correlation, so we used the Greek letter rho in the past to mean correlation. The correlation between two random variables is equal to b sub ij. Name those two random variables. I will give you one. Z sub j. So before we had seen the correlation between two random variables was equal to lambda. What were the two random variables? Z and F. Okay? So what am I going to have here? Correlation between Z and F star. Because F star now is this new common factor, essentially. So let's apply these ideas now to the goblet data set. Here's the old goblet diagram to help you see what's going on. And I'm going to use the Varimax method with this. Excuse me. We're going to use exactly the same code as before. I'm going to put the results into mod.fit2v to stand for Varimax. The only difference is that before we had rotation equal none as an argument. Now I'm going to have rotation equal Varimax. I'm going to print off the result. And you can verify on your own, the only thing that changes in all the output is now your factor loading. So essentially this would be lambda star, or essentially too, you could call it B. Let's put a hat on top of the stuff. And so here's my new factor loading matrix, which will allow me to come up with a new interpretation of what my factor analysis model represents in comparison to what we had previously. So notice, for example, here, due to the rotation, this loading on the first common factor for W6 is essentially 0. And so the remaining variables, 1, 2, 4, and 5, notice what they're looking at. The width of the goblet. So the first common factor is essentially a measurement of the overall width. Before we kind of said the overall size, because with the previous factor analysis model, a W6 played a role, but now it no longer does. So this is just a measure of just the width. How about common factor number 2? How would you interpret that? Without hopefully looking at my notes, which has the answer in it on page, page 38. Don't look. How would you interpret common factor number 2? So notice I have very small values for W1 and W2, so that's good. We can essentially kind of ignore them. And we just have W4, W5, and W6. So common factor number 2 represents what? Essentially the base. Okay. This is a little bit easier interpretation than what we had previously with the original factor analysis model that we had. So if I were to ask you then to actually write out the model, this is what we would get. Notice what's different here from what we had before. I have stars here for our common factors, and also I have this different factor loading matrix in there from what we started off with at the very beginning of class. Very briefly here, I do want to mention that if I were to do the same plot of those factor loadings that we had saw about 10 minutes ago, this is what I would get. And let's do a split screen here. Let's compare that to what we had before. So this is what we had before. And you can see that W1, W2, W5, W4, and W6 are relatively in the same location that we had seen there when I had drawn those red lines. Now, for this different XY coordinate system, the only difference is that W6 is up here rather than perhaps down here. And the reason why this happens is that there's actually more to this geometric or graphical approach to doing this, and you have what's often called a reflection that you have to worry about. So essentially W6 has been reflected up in the plot. I'm not going to ask you a question about that. I just wanted to bring that to your attention in case you are looking through the notes and you're wondering, why is that occurring? Okay. Now there are other kinds of rotation methods out there that are not orthogonal. They're called oblique. What that means is the following. Suppose I were to do a plot. I guess I can come over here and do it. Suppose I were to do a plot of these factor loadings. And let's say the loadings ended up being, maybe like this. Okay? Now, if I do a rotation of my x and y axis, I'm not going to quite be able to get the x and y actual axes to go through all those points. So what an oblique rotation then does is this. Consider a rotation that changes your x and y axes so they're no longer orthogonal. That's what an oblique rotation does. The problem with doing an oblique rotation. The reason why I don't talk about it in our class is it violates some of the underlying assumptions of our model. In particular, that our common factors are independent of one another. Independence in a matrix algebra setting is essentially expressed as orthogonal, without getting into all the details. And so this actually violates a model assumption, so that's why I do not talk about it. But I at least want to tell you that it is out there. So the last part then of this factor analysis section is to talk about factor scores. Factor scores are essentially the equivalent to what we did with principal component analysis when we found principal component scores. A factor analysis score is numerical values for our F, or our F star. I want to find numerical values, estimates, for these unobservable random variables. And there are two ways that you can do this. I'm going to talk about them briefly. Unfortunately, to fully understand them, they require a background in Stat 970, our linear models class here. I guess one of them is more of a Stat 870, our regression class. And so I'll make some comparisons to that, but whenever I say Stat 870 or Stat 970, you're not responsible for it in this class. Okay, so the first method is called Bartlett's method. It's also often referred to as weighted least squares. And simply it's this. For, let's say, your rth observation and its standardized values, take a look at this little expression here. Z minus a gamma hat times F transpose times your psi hat matrix. It's a diagonal matrix with the specific variances on the diagonal. Psi hat inverse. And then you take Z minus gamma hat times F once again. You could put gamma star in there with an F star too. It's just, it doesn't, I don't think I need to rewrite it for that purpose. And so you can see here, essentially what we have here is kind of like what you would see in regression analysis, a residual. Let's say y minus x times beta hat. Essentially that's what it is. And because of that, then, if you want to try to, let's say, minimize this, what ends up being a weighted residual, because we have that variance matrix in the middle there, you can use what's called weighted least squares that would be taught in Stat 870 and also Stat 970 to find what the value of f will be that minimizes this expression. You're only responsible for understanding that this is the value of f that minimizes it. So it's, just a product of some matrices. Some are transposed, some are inverted. You can easily program this into R. It's not that difficult to do. And that's how you would find it for, let's say, the rth observation. And you would do this then for every observation in your data set to find a factor score. The second method is called Thompson's method, also known as the regression method. If you take in a Stat 970 class, you typically spend some time talking about, suppose your response variable y and your independent variables x are all random variables. And how do you find then the parameter estimates for your regression model if both y's and the x's are random variables? What ends up happening is that your parameter estimates end up being exactly the same as if you were to assume the x's are constant, which is usually the case that one begins with, like in a Stat 801 class. And so what one can do then is consider then a joint vector between z and f. Consider them as both random variables. I just put all the z's first and I put all the f's below it. And its corresponding distribution, if we had an underlying normal distribution, its corresponding distribution is multivariate normal as well. A mean vector of 0. So essentially I took the mean of the z's, I put a 0 there. I took the mean of the f's, I put a 0 there. Just kind of stacked them together. And then the covariance matrix is this. The covariance of z, which we've already seen before, is P. The covariance matrix for f is I, the identity matrix, which we've seen before. And then the covariance between the z's and the f's, if you remember, are the lambdas. So this is kind of just a block matrix here, to use some common terminology. And again, to use some stuff that one would learn about in Stat 970, one could find the expected value of f, given some observed value for z. And you would find that to be lambda times P inverse times Z star. For those of you who had Stat 970, compare this to what you would have for, let's say, expected value of Y conditional on X. Please make that small change there. I didn't think it really added anything, maybe even confused the issue, so that's why I deleted some text there, and I made some small changes also in blue. Using this expression, what we have here is what would we expect F to be if I have a particular set of standardized values. That seems like a reasonable thing to use then to come up with an estimate for F. So what I would call then F hat for the rth observation then is, well, here's my gamma hat. Actually, that should be a prime up there. I put an estimate for gamma in there. Here's my Z, essentially. And then, because my factor analysis model has a particular representation for P, I can put in what its corresponding estimate would be that we saw before when we were dealing with residuals. And that will be my factor score using this particular method. Okay. So we are out of time. What we will start off with next time then is, real briefly, we'll talk about how we can find these factor scores in R. And note that the test itself, this test number 2, will go up until page 46. So we'll cover this entire factor analysis section. But it won't cover anything else that we might talk about during our next class. Are there any questions? Okay, that's it for today.